faithfully delivering value, we explore the world's great books. Hello, this is Sally's Book Talk. Today, we're diving into the book, The Fascinating Temperature, with the subtitle, The Human, Earth, and Cosmic History in a Thermometer. Every morning when we wake up, most people think about a few questions. What time is it? What's the temperature today? And where am I headed later? Unconsciously, measurements of length, time, and temperature shape our lives. Over the past few thousand years, human understanding of length and time hasn't changed much. But temperature is a whole different story. Even a baby can tell hot from cold, but we've only figured out how to measure temperature for a few hundred years. Nowadays, the most common temperature scale globally is Celsius, where water freezes at 0 degrees and boils at 100 degrees. But back in 1742, when Swedish astronomer Anders Celsius first proposed his scale, he actually set water's freezing point at 1 degree and boiling point at 0 degrees, totally opposite to what we use today. Why do you do that? Because temperatures in Sweden often drop below freezing. Celsius did this to avoid negative numbers in temperature records, but the colder it got, the higher the reading, which is kind of counterintuitive. So within a couple of years, people flipped Celsius as 0 and 100 degrees, creating the Celsius scale we know today. Um, Turns out, behind the familiar concept of temperature, there are tons of hidden fun facts and discoveries. This book, The Fascinating Temperature, digs into some of these temperature-related mysteries. The author, Gino Segre, is an American high-energy particle physicist honored by the National Science Foundation and the Department of Energy. He comes from a family of physicists. Many in his clan were scientists, like Emilio Segre, who won the Nobel Prize in Physics. After over 30 years in physics, author Gino Segre looked back on his career and his father and uncle's lives, realizing many scientific themes revolve around temperature. For humans, which temperatures are super important? In this book, the author starts from 6 key sets of temperature data, guiding us to uncover the mysteries of life and the universe. These 6 sets are animal body temperature, the temperature of civilization, the temperature of enlightenment, deep sea temperature, the sun's temperature, and the limits of temperature. First up is animal body temperature. Why do some animals maintain a constant body temperature, and how do they keep warm? From the Inuit on the Arctic ice to brokers on the New York Stock Exchange, human body temperatures are strikingly similar. We often say the human body temperature is about 37 degrees, but this isn't very precise because temperatures vary throughout the body. Skin temperature is usually 6 degrees lower than internal organs, and different organs have slight variations depending on metabolism and blood flow. Besides humans, there are also many warm-blooded animals in the animal kingdom that maintain constant body temperatures. So, what exactly are the benefits of being warm-blooded for animals? So let's imagine a scenario. An ancient human ancestor being chased by a lion on the African savanna. As prey, our ancestor needed to coordinate limb movements while fleeing, and the brain had to calculate the best survival strategy. Should I run left or right, climb a tree, or jump into a river? Thoughts in the mind and physical actions must be synchronized to chart a path to survival. On the other hand, the hunting lion also needs to make many judgments. Is this animal edible? Can I catch it? Both humans and lions want to survive and pass on their genes. To achieve this, they both have to make several decisions simultaneously. And the brain is at the core of these decisions. Whether human or lion, the brain contains an astonishing number of neurons. The transmission and reception of neural signals rely on complex chemical reactions that require a specific temperature to occur. Generally, the higher the temperature, the faster chemical reactions proceed. So setting a higher body temperature makes internal reactions more active, but it can't be too high. If excess heat can't be dissipated and incoming information arrives too quickly, the system crashes. Just like some computers are prone to crashing in summer, over millions of years, humans and other warm blooded animals have discovered a common pattern around 38 degrees Celsius. Our thoughts and actions are most efficient. Therefore, from an evolutionary perspective, maintaining a constant body temperature helps enhance physical functions and increases our chances of winning in the survival competition. That, perhaps for this very reason, warm blooded animals, including humans, became the dominant species on land. So, how do warm blooded animals maintain a constant body temperature? To keep body temperature steady, efficient cooling and warming mechanisms are equally important. Warm blooded animals mainly prevent overheating by sweating, fanning, and panting. If the outside temperature drops too low, we generate heat by shivering. And in long term cold environments, warm blooded animals develop thick fat to insulate against the cold. Penguins and seals are perfect examples. Some seals have about 6 millimeters of fat under their skin. Thanks to this layer, their internal temperature is a full 21 degrees Celsius higher than their skin temperature, so they can brave the Arctic cold. Besides fat, penguins have another warming trick: huddling. Emperor penguins are the classic example. When blizzards strike, emperor penguins spontaneously cluster in groups to stay warm. The outer penguins rotate shifts. Each massive group has tens of thousands of penguins, even hundreds of thousands at peak times. Through collective strength, they endure Antarctic cold that plummets to tens of degrees below zero. If body temperature regulation fails, people get a fever. Actually, we don't fully understand the exact mechanism of fever yet. The medical world once thought, rising temperature was to kill invading germs. But for most bacteria, the lethal temperature is far higher than what humans can tolerate. And that's why sterilizing medical tools and cooking meat require temperatures above 70 degrees Celsius. So, if the purpose of rising temperature isn't to kill bacteria, then what is it? Unfortunately, we haven't found a definite answer to this question yet. What is the root of body temperature control? How is it set and how does it change? Scientists are just starting to study these basic questions. The journey of science and civilization is all about asking questions and seeking answers. Speaking of civilization's development, besides using familiar timelines, we can also use temperature to define it. This special measure, from hunting and gathering to settling villages to tool production, human-made temperatures start from 0 degrees, go through 500, 1,000, 2,000 degrees, up to hundreds of millions of degrees. Differing and characteristic civilization have distinct signature temperatures. We don't know which Homo sapiens ancestor first mastered life skills, nor do we know where the first fire was kindled. But one thing is certain: fire transformed human lifestyles. Blazing bonfires could scare away wild beasts while bringing light to caves. This allowed our ancestors to settle deeper in caves. With fire, humans could migrate from tropical and temperate zones to harsher climates. In the severe frigid zones, they even began using fire to process metal and create efficient tools. As technology advanced, fire temperatures rose higher, moving civilization from the primitive Stone Age through the glorious Bronze Age to the Iron Age, where smelting required 1,400 degrees Celsius. Humans achieved this temperature about 2,000 years ago, making 1,400 degrees Celsius the hallmark of the Iron Age. Yet for over a millennium afterward, fire-making technology saw little progress. It wasn't until the 18th century invention of the steam engine that the world changed again. This history remains deeply intertwined with temperature. No lacking a specific temperature marker, the steam age's birth relied on humanity's grasp of temperature's essence. Scientific exploration of temperature birthed thermodynamics, revealing the first law. Heat is energy, and energy is conserved. Steam engines converted thermal energy to mechanical power, launching the steam age. After its explosive growth, humanity entered today's nuclear age. In 1994, Princeton Plasma Physics Laboratory's fusion reactor reached 510 million degrees Celsius using magnetic confinement. This remains humanity's highest controlled temperature, while uncontrolled fusion can hit billions of degrees, like in a hydrogen bomb's exploding core. Now, with deeper understanding of heat, scientists look ahead. What will Earth's future hold? Will it scorch or freeze? And what about humanity then? Next, we explore Earth's temperature, crucial to human fate. Newborn Earth was a scorching fireball. As temperatures cooled, liquid water formed, and life emerged. After billions of years of evolution, humans finally appeared on Earth. Undoubtedly, humanity's fate is deeply intertwined with Earth's temperature. If Earth's temperature rose or fell by 100 degrees, humans couldn't survive. Even smaller changes of just a few degrees would significantly impact human life. The biggest factor determining Earth's temperature is its motion relative to the sun. Astronomers tell us Earth orbits the sun in an elliptical path at a tilt, but many don't know this orbit isn't a perfect ellipse. Its eccentricity fluctuates, meaning sometimes the oval becomes more elongated than usual. So Earth's distance from the sun varies yearly. Closer some years, farther others. Affecting temperature, like moving away from a stove, reduces heat. When Earth is farthest from this solar furnace, it enters an ice age. Calculations show 9 major ice ages occurred over 650,000 years, with summer temperatures 7 degrees lower than now, blanketing Earth in ice like in ice age films. Land frozen, life dormant. Fortunately, we're in a warm interglacial period, allowing civilization to flourish. Historically, these last 20,000 years, ours began 11,000 years ago. So, while ice ages remain distant, the urgent threat is global warming from the greenhouse effect. French mathematician Fourier first proposed the greenhouse effect in the early 1800s, though he didn't know CO2 traps most heat. Today, rising atmospheric CO2 concentration is widely considered the primary driver of global temperature increase. But how high will it rise? That depends on population growth rates and, crucially, how people live. Industrial production emits far more CO2 than slash and burn agriculture ever did. Globally, more industrialized nations have higher per capita CO2 emissions. Certainly, continued warming will raise sea levels, dooming coastal cities as oceans unleash catastrophe. But at the same time, the ocean is also a sanctuary for life. Why do we say that? Despite Earth's catastrophic events, life has always persisted. This may relate to ocean temperatures. Many assume the sunless deep sea is a pitch black, freezing hell. But a 1979 deep sea expedition shattered this perception. Scientists in a submersible discovered hydrothermal vents in the Pacific trenches. These hot springs erupting from seafloor cracks create temperatures exceeding 350 degrees Celsius. And they describe these fissures as gateways to hell. Sulfur-rich waters from Earth's depths cool rapidly in the ocean, depositing calcium sulfate that builds chimney-like structures. Temperature differences between vent water and surrounding seawater can exceed 300 degrees Celsius within centimeters. Nature's most extreme thermal gradient. Scientists later made a stunning discovery: bacteria thriving on these chimneys, a revelation that defied all expectations. In daily life, high temperature sterilization is common practice. We cook meat above 70 degrees Celsius to kill bacteria, yet vent bacteria flourish at 80 degrees Celsius and beyond. The current high temperature record holder is Pyrola famarii, thriving at 110 degrees Celsius. It can't reproduce below 90 degrees Celsius. Many other bacteria survive near 100 degrees Celsius, collectively called Thermophiles. Some propose subterranean thermophiles exist in unimaginable numbers, perhaps matching all surface bacteria combined. These bacteria revolutionized our understanding of life. Humans tolerate around 37 degrees Celsius. Beyond 41 degrees Celsius, our systems fail. Even at that threshold, we survive briefly, yet thermophiles thrive in sunless, toxic, superheated depths. Why? While surface life depends on solar energy, plants photosynthesize oxygen and carbohydrates, animals consume them. Vent thermophiles developed an entirely different mechanism. As mentioned, deep sea vents spew sulfur rich water. Thermophiles react chemically with sulfur atoms, generating energy to produce carbohydrates. Simply put, around these vents, chemosynthesis replaces photosynthesis as life's foundation. Beyond thermophiles, psychrophiles thrive near freezing temperatures, even in icy water. These extreme loving microbes reveal new possibilities for life. If climate crisis strikes, thermophiles could become life's embers. Even if land freezes without sunlight or oceans flood continents, chemosynthesis could sustain life at hydrothermal vents. When climate stabilizes, they might even recolonize land. Over billions of years, the Earth endured cataclysms, yet life never truly vanished since its birth. Perhaps this is why. Earlier, we noted surface life uses solar energy, most generated in the sun's core. Over millions of years, this energy radiates outward. The sun's core is a nuclear reactor. Every second, 1 trillion pounds of hydrogen nuclei fuse into helium, releasing colossal energy, which nuclear reactions catalyze this hydrogen to helium transformation. And how fast do they occur? This all depends on the sun's core temperature, impossible to measure directly. Fortunately, we receive messengers from the sun's heart that reveal its temperature. They're called neutrinos, elusive particles, invisible, intangible, chargeless. These properties allow neutrinos to escape the sun unimpeded, traveling to Earth and beyond. In 1930, Austrian physicist Wolfgang Pauli proposed neutrinos. Later, American Hans Bethe developed the standard solar model using sun's mass radius. In this model, the sun's core temperature directly correlates with neutrino production. The hotter the sun's core, the more neutrinos it produces, and vice versa. So by measuring neutrino counts, scientists can calculate the sun's core temperature using the standard model. But how do we detect these elusive particles? Neither Pauli nor Bethe provided answers. Years later, physicist Enrico Fermi proposed that rarely a neutrino could transform an uncharged neutron into a positively charged proton. Countless neutrinos pass through neutrons constantly. Perhaps one such change occurs occasionally. Based on this principle, scientists built neutrino detectors using a common household item: laundry detergent. Detergent's main component is perchloroethylene. Neutrino detection relies on its chlorine atoms. As mentioned, neutrinos have minuscule odds of transforming a neutron into a proton. In vast oceans of chlorine atoms, some occasionally encounter neutrinos. When this occurs, a neutron in the chlorine atom becomes a proton. By detecting how often this happens, scientists estimate neutrino counts and thus the sun's core temperature. In 1968, American physicists built the first large neutrino detector in an underground gold mine. Essentially, it was a swimming pool filled with detergent. Detergent wholesalers thought their bulk buyer ran laundromats, yet this pool revealed the sun's core temperature, about 15.7 million degrees. This data helped scientists better understand solar fusion reactions. Beyond the sun, other stars release distinct neutrinos when burning or collapsing. Using these tiny messengers, we probe distant stars' temperatures, uncovering the universe's past, present, and future. Thus far, we've explored temperatures across the cosmos. So in the vast universe, does temperature have limits? According to current models, the Big Bang's inception marked the universe's hottest moment, reaching hundreds of billions of degrees. To this day, neither space nor human labs have recreated such infernal heat. In contrast, The lower limit of temperature in the universe seems more approachable. The absolute lower limit is absolute zero, specifically minus 273.15 degrees Celsius or 0 Kelvin. But note, this limit is theoretical, impossible to reach, only approach infinitely. Temperature measures the kinetic energy of particles like atoms and molecules. Higher energy means higher temperature. At minimum kinetic energy, complete stillness, temperature reaches absolute zero, a silent world where atoms freeze, existing only theoretically as an unattainable extreme. Over the last 2 centuries, scientists have marched toward this lower limit in labs. Along the way, they've made unexpected discoveries. For example, at negative 269 degrees Celsius, Mercury's electrical resistance suddenly vanishes. Above this temperature, resistance abruptly returns. This is superconductivity. MRI machines in hospitals use superconducting magnets. Superconducting materials also enable large physics experiments like particle accelerators and fusion reactors. Due to cost and environmental constraints, superconductivity remains rare in civilian use, but its potential is immense. Superconducting wires and transformers could drastically reduce power transmission losses. Superconducting computers could boost speeds 10 to 100 times, with active research in maglev trains and ship propulsion systems. As a branch of modern physics, low-temperature physics has secured an indispensable position. Pursuing temperature extremes mirrors humanity's scientific perseverance. Now, let's review the fascinating temperature. Authored by theoretical physicist Gino Segre, it explores life and cosmic mysteries through 6 key temperature datasets. These 6 are animal body temperature, civilization's temperature, Earth's temperature, deep sea temperature, the sun's temperature, and temperature limits, where body temperature reveals evolutionary secrets and civilization's temperature connects to technological progress. Why do some animals maintain a constant body temperature? And how do they keep warm? From the Inuit on the Arctic ice to brokers on the New York Stock Exchange, human body temperatures are strikingly similar. We often say human body temperature is about 37 degrees, but this isn't very precise because temperatures vary throughout the body.
Yes.
Skin is usually 6 degrees cooler than internal organs, with slight variations depending on metabolism and blood flow. Besides humans, many warm-blooded animals in the animal kingdom also maintain constant body temperatures. So, what exactly are the benefits of being warm-blooded for animals? Let's imagine a scenario. An ancient human ancestor being chased by a lion on the African savanna. As prey, our ancestor needed to coordinate limb movements while fleeing, and the brain had to calculate the best survival strategy. Should I run left or right, climb a tree, or jump into a river?